Good day everyone and welcome to our lecture on group 15 elements. The elements in this group are also referred to as pnictogens, and they include nitrogen, phosphorus, arsenic, antimony and bismuth. With the exception of nitrogen, which appears as a gas, all the others are solids. Their common electronic configuration is Ns2p3, and so you can either add electrons or remove electrons to easily achieve a noble gas configuration. As such, there are many oxidation states available for these elements. For example, nitrogen can exist in all oxidation states ranging from -3 to +5. Nitrogen forms very strong multiple bonds to itself and neighboring elements belonging to the same row. For example, you have the cyanide anion, the dinitrogen gas itself, which is an inert gas, and you have the nitrosyl cation. The coordination number increases down the group. For example, nitrogen would form mainly 3 or 4 coordinate species, whereas phosphorus can form 3 to 6 coordinate species. With the exception of nitrogen, the ability to form covalent chain-like compounds, which is called catenation, decreases down the group. In general, it is very difficult to rationalize the properties of these elements. This slide summarizes selected physical properties of these elements. As you can see for the melting point, there doesn't seem to be any particular trend. An exception is arsenic, which actually doesn't show a melting point, but sublimates at 614 degrees. The boiling points seem to increase down the group. Again, arsenic is an exception. Since it sublimates, it has no boiling point. As expected, the sizes of these elements increase down the group, and the first ionization energy decreases down the group. The electronegativity of these elements also decreases down the group. Because of their diverse properties, these elements form compounds of very different reactivity. For example, dinitrogen is an inert gas. Phosphorus is a very reactive nonmetal with at least 3 allotropes, and arsenic and antimony are metalloids and well-known poisons. Bismuth is a metal and a replacement for lead in electronic solders. In this depiction, you can see different allotropes of phosphorus, and you can see that they come in different forms and colors. Now let's look at nitrogen in more detail. Nitrogen was independently discovered in 1772 by a range of scientists. These include the German-Swedish pharmacist Carl Scheele, English chemist Henry Cavendish, who also discovered hydrogen, and Joseph Priestley. Scottish botanist Daniel Rutherford also contributed to this discovery. The air contains 99% of all nitrogen found on Earth as dinitrogen. In salts, it mainly exists as nitrates, NO3-, and the majority of nitrogen compounds are covalent except for those based on the nitrite ion, which is the N3- ion. Industrially, nitrogen is obtained by fractional distillation from air. Liquid nitrogen boils at -196 degrees Celsius and is routinely used in labs. Ammonia is certainly one of the most important chemicals for humanity. It is a pungent, colorless gas and toxic at high levels of exposure. It contains the nitrogen in the -3 oxidation state, and ammonia contains a sp3 hybridized nitrogen center. As such, it exhibits a distorted trigonal pyramidal structure. Ammonia undergoes a very rapid inversion with a rate of 2.4 times 10 to the power of 10 per second. In this depiction, you can see the inversion. Essentially, the lone pair, which initially sits on top in this depiction, will flip to the other side, and essentially this inversion resembles an umbrella that flips to the other side in the wind. Ammonia is both a Lewis and Bronsted base, and it is also reducing. The applications of ammonia are manifold. 80% of all ammonia produced is used for fertilizers. It is a starting material for nitrogen-containing compounds, for example polymers like nylon, explosives, paints, coatings, pharmaceuticals, and many, many more. It is also used to kill germs in meat processing, and if you want, you can go to this webpage and read about a controversy with regards to this application. How is ammonia produced? It is produced by the so-called Haber-Bosch process, whereby you simply take dinitrogen and dihydrogen and convert them to ammonia. Now, this seemingly very simple reaction is very difficult to achieve. Here you can see the thermodynamic data at 298 kelvins. It has a delta G of -33 kilojoules per mole, which means it is a reaction that should be possible. It is also exothermic with -92 kilojoules per mole, However, it is entropically very disfavored. So you have a reaction entropy of minus 198 joules per mole. Again, this is quite easy to understand. Since you are converting 4 gas molecules into 2 gas molecules, you are essentially decreasing the entropy. Nevertheless, the process is still viable, and you have to conduct it at high temperature of 460 degrees Celsius to reach the activation energy. You also need high pressure of 100 atmosphere, and you need the presence of catalysts, which for example consists of a mix of iron oxide, potassium oxide, silicon oxide, and aluminum oxide. The Haber-Bosch process is probably the most important technical process. It consumes about 1% of all human use energy. And take note that about 40% of nitrogen atoms in an urban human, which means all of us, went through this process. Without this process, the world population would drop to pre-industrial level of about 2 billion in about 2 years. Currently, the world population is about 7.8 billion. Another very important compound is hydrazine. Hydrazine has a formula N2H4, and it contains the nitrogen atom in a -2 oxidation state. It is a toxic oily liquid at room temperature and can be viewed as an amino derivative of ammonia. So essentially, you are replacing one hydrogen in ammonia with a NH2 group. It can be obtained by oxidation of ammonia, usually using hypochlorite or hydrogen peroxide as the oxidant. Here you can see the equation. So you have hypochlorite that reacts with ammonia, which contains nitrogen in a -3 oxidation state, to hydrazine, and in addition you produce water and the chloride anion. Hydrazine is used as a rocket fuel and as a precursor to other nitrogen compounds. It is thermally unstable, and so you can decompose it into ammonia and dinitrogen. When hydrazine is used as a fuel, it gets oxidized to dinitrogen and water. Here you can see the Lewis structure of hydrazine, and so you have a free rotation around the NN bond as depicted here. In addition, each of the nitrogen still contains one lone pair. So the molecule undergoes internal rotation around the NN bond. Another interesting compound is Hydrazoic acid. This Hydrazoic acid contains the N3- anion. The acid is volatile, it boils already at 37 degrees Celsius, and it is a highly toxic and explosive liquid. This reactivity is highlighted in this equation, whereby 2 molecules of Hydrazoic acid would decompose to dinitrogen and hydrogen. It is prepared by protonation of azide salts, which in turn are prepared by the reaction of nitrous oxide with amide. You can see the reaction. Again, 1 molecule of nitrous oxide reacts with sodium amide to form sodium azide and water. Then subsequently, the sodium azide is simply protonated by a strong acid to form the hydrozoic acid. And in addition, you eliminate sodium chloride. Heavy metal azides, those of mercury, lead, silver, or cadmium, are explosive and can detonate on heating or by mechanical shock. The azide anion has several resonance structures which are depicted here. So essentially you are just varying the charges at the nitrogen atoms. And since you have 3 nitrogen atoms, you can have a variation of these charge distributions. Overall, this gives rise to a linear triatomic molecule. Interestingly, azides are used in airbags. The airbag of a car contains several inorganic compounds, including sodium azide, potassium nitrate, and silicon dioxide. On head-on collision, a signal from the deceleration sensor ignites the gas generator mixture by an electrical impulse, creating the high temperature condition necessary for sodium azide to decompose to nitrogen gas, which fills the airbag. The simple decomposition of sodium azide into sodium and 3 equivalents of dinitrogen is shown here. Subsequently, the sodium is converted to less dangerous sodium oxide by reacting with potassium nitrate. So 10 equivalents of sodium react with 2 equivalents of potassium nitrate to form 5 equivalents of sodium oxide, potassium oxide, and dinitrogen is released again. The basic metal oxides then react with the acidic silicon oxide to produce stable silicates according to the following reaction, whereby 2 equivalents of sodium oxide reacts with silicon oxide to form the sodium silicate. Overall, you have a lot of redox chemistry happening in an airbag. There are numerous nitrogen oxides that contain nitrogen in different oxidation states. Nitrous oxide, which is also known as laughing gas, contains nitrogen in a +1 oxidation state. Nitric oxide, dinitrogen trioxide, nitrogen dioxide, dinitrogen tetroxide, and dinitrogen pentoxide contain nitrogen in higher oxidation state from +2 all the way to +5. Now we look at another very important element of this group, which is phosphorus. Phosphorus was discovered by the alchemist Henning Brandt in 1669 in quest for the philosopher's stone, which would convert cheap metals into gold. Interestingly, he collected urine and evaporated the golden urine to dryness, and subsequently he distilled the residue in the absence of air and obtained a material which glowed in the dark. The name comes from Greek word phosphorus, which means carrier of light. The phosphate in the urine, which has this particular formula, has been reduced to white phosphorus by carbon, which is also formed from the organic residue present in urine. There are overall three main forms of phosphorus, which are the white, red, and black phosphorus, forming a wide range of cages and rings with pp single bonds because of the favorable pp single bond energy. Phosphorus has strong affinity to oxygen and does not naturally exist in its elemental form, but only as derivatives of phosphoric acid, which are known as the phosphates. The most important natural phosphate is apatite. It has this particular formula, so it is actually a calcium phosphate with a second anion X, which could be hydroxide, chloride, or fluoride. So dependent on the second anion, you could have hydroxyl apatite, chloroapatite, or fluoroapatite. Teeth and bones of vertebrates contain phosphorus as hydroxyl apatite, which is also known as enamel. In this slide, we are comparing the different forms of elemental phosphorus. White phosphorus is highly reactive and toxic and is produced by reducing apatite with charcoal and quartz at 1400 to 1500 degrees Celsius according to this reaction. So 2 equivalents of calcium phosphate is reduced by 10 equivalents of carbon in the presence of 6 equivalents of silicon dioxide to a calcium silicate and 10 equivalents of carbon monoxide and white phosphorus. Red phosphorus is made by heating white phosphorus to 250 degrees Celsius or simply by exposing it to sunlight. Black phosphorus, which is polymeric, is denser than white P4. Accordingly, it is produced by subjecting white P4 at 200 degrees Celsius to a pressure of 1200 megapascal. Here you can see the molecular structures of white phosphorus, which is a tetrahedral consisting of 4 phosphorus atoms. Red phosphorus is a linear polymer, and black phosphorus is a more complicated polymer. Red phosphorus is used in matches. Here we will look at the chemistry of matches. Safety matches were invented in 1848. On each side of the abrasive strip of the matchbox, you actually have red phosphorus, which is mixed with powdered glass. On the other hand, the head of the match contains antimony sulfide or sulfur as reducing agents and potassium perchlorate as a strong oxidant. Now, when the match is rubbed along the strip, some of the red phosphorus is rubbed off, and at high temperature it ignites with the chlorate in the flammable head, leading to ignition of the matchstick. And here you can see the reaction that occurs in the head of the matchstick, whereby 4 equivalents of potassium perchlorate reacts with antimony sulfide, form 4 equivalents of potassium chloride and an antimony sulfate. Phosphorus also forms a compound with hydrogen which resembles ammonia, and this molecule is called phosphine. Phosphine is a colorless, highly flammable and highly toxic gas. It can be prepared by reacting white phosphorus with hydroxide. According to this reaction, 3 equivalents of water reacting with P4 and 3 equivalents of hydroxide to form phosphine and 3 equivalents of dihydrogen phosphate. The successive substitution of the hydrogen atoms in pH3 with alkyl or Ara groups leads to a wide range of organophosphines, PR3, that form a very important class of ligands in organometallic chemistry and catalysis. So phosphine ligands are neutral 2-electron donors. They are excellent soft ligands with a wide variety of easily adjustable steric and electronic properties. So essentially you can vary these R groups and therefore achieve a huge variety of different types of phosphines. Phosphorus reacts with oxygen to form different types of oxides, which can give rise to oxoacids of phosphorus. For example, P4 would react with dioxygen to form P2O3 or more precisely P4O6. Further oxidation with dioxygen would give rise to P2O5, or more precisely P4O10. Here you can see the molecular structures of the tetrous phosphorus hexoxide or the tetraphosphorus decaoxide. You can see that the oxidation state of the phosphorus is different in these two phosphorus oxides. These are the anhydrides of acids, and so if you treat P2O3 with 6 sequence of water, you obtain phosphonic acid. If you treat P2O5 with water, then you get phosphoric acid, which structure are depicted here. Phosphoric acid can also be condensed into polyphosphoric acid, and that happens through elimination of water molecules. So 2-orthophosphoric acid, which is the typical phosphoric acid, can eliminate water to form diphosphoric acid of the formula H4P2O7, which is also called pyrophosphoric acid. Now, if you continue doing this condensation, you obtain a polymer, which is then known as polyphosphoric acid. So heating phosphoric acid results in the condensation of the molecules with elimination of water to form dimers, trimers, and higher polymers of phosphoric acid. With this, we come to the end of the lecture on group 15 elements.